finding the area under a curve is the ultimate purpose of integration, and it's sort of the definition of what the integral is and why we use the notation that we do. So we're going to start with some examples of that, and then we're going to try and develop the basic idea behind it. The same way as we did a first principles derivative, we'll do a first principles integral at the end once we've done a few examples. So the first thing we need to be able to get through before we can do areas under curves is the idea of an iterated integral. Let me write that down for you. An iterated integral. Okay, so if I were to take this integral here, the integral of x squared plus 2 dx, and I was going to make it an iterated integral, what I would add to that are two numbers. One at the bottom of the integrand here. Let's go from, let's say, 2 all the way up to 5. So what this is doing ultimately is asking me to find the area between the x-axis and the function x squared plus 2, between the x values of 2 and 5. Now that was a lot of information, and I will spell that out a little more when we actually do an area under a curve example. I just want to show you how to handle this before we get into anything too terribly theoretical. So the first thing we're going to do is actually integrate x squared plus 2. So that would be, well, what would give me an x squared? An x cubed would. And in order to get the coefficients to match, I'd need a 1/3 there. 3 times a third is 1. And then to get this thing, I'd need a 2x. And then anytime you integrate, you have a constant at the back. And you notice that this information here between 5 and 2 has kind of been lost when I did that integration. To show that it's still iterated, right? That iterated just means between 2 points. I'm going to take the s there. I'm going to stretch it out because they actually did the integration. Stretch it out. And then you keep those two numbers on there. The 5 on top and the 2 underneath. So what this is asking you to do is to take your answer and sub in 5 for x. Then you're going to take your answer and you're going to substitute in 2 for x. And then you're going to find the difference between them. So if I were to write that in English to you, this little symbol says, find the difference between the answer evaluated at 5 and the answer evaluated at 2. So if this had been a 7 and this had been a 3, that would be 7 and that would be 3. Right? I'm just plugging the numbers in now. So if I were to actually execute that, I would have 1/3 of 5 cubed plus 2 times 5 plus whatever this constant is. And I'd have to subtract from that 1/3 of 2 cubed plus 2 times 2 plus c. So if I actually do that, 5 times 5 times 5 is 125. That's 125 thirds. 2 times 5 is 10, plus this constant, which I still don't know a value of. Turns out it doesn't matter. 2 cubed is 8, so that's minus 8 thirds. Subtract 2 times 2 is 4. Subtract this constant, whatever that is. And you'll notice something interesting happening. These constants, it doesn't matter what that number was, it vanishes. So what I've got left then is 125 thirds minus 8 thirds is 117 thirds. Plus 10 minus 4 is plus 6. That's 18 thirds. 18 and 117 would be 127, 135. And I think that is 45. Yeah, equals 45. That's fine. Okay. So when you see this iterated integral, it just asks you to do the integration like you normally would. And once you're done, you sub in the top number, sub in the bottom number, right? Like I put the 5s in, I put the 2s in. And then once you get your answer, you subtract the 2 from each other. And that gives you a number answer instead of a function answer. So I'm going to erase this. I'm going to come up with another example. We're actually going to sketch it so you can see how an integration is related to the area underneath of a curve. So I've given you a function. It's barely a function, g of x equals 3. And I've asked you to calculate the area between g of x and the x-axis between the values of 2 and 6 on the x-axis. So in order to get an idea of what we're talking about, I'm going to sketch it for you. So I'm going to need an x-axis then, like so. 1, 2, 3, and 1, 2, 3, 4, 5, 6. So this function, g of x equals 3, that means that this line has a height of 3 regardless of what x I'm at. So it's going to look like this. There's g of x. I suppose it goes in both directions. And I've been asked to find the area between this line and this axis, between x is 2 and x is 6. 2, 3, 4, 5, 6. Okay. Now, this shouldn't be too challenging. I mean, if I look at this shape here, that's just a rectangle. And the area of a rectangle is its length times its width. It happens to be 1, 2, 3, 4 units long. It happens to be 3 units high. So the answer should be 12. Now, that's not calculus. That's just grade 9. Maybe even before that. But what I'm trying to do now that I have an answer is to connect the area under a curve to an iterated integral. So the idea is that the area between a curve and the x-axis can be calculated by integrating that function between an x value of 2 and an x value of 6. So right now, I mean, you're wondering why am I using integrals to do this when I can just draw a rectangle? Very shortly, we're going to get into curves that are not rectangles and are not triangles and are not circle segments, which means you can find the area under anything if you can do this. So this is the more powerful tool than memorizing area and volume formulas. We just sort of have to build up to it. So if you can just humor me for a minute and we integrate this. So what function has 3 as its derivative? Well, that would have to be 3x plus the constant. And I'm supposed to be evaluating this thing from 6 to 2. So if I actually do that, I fill in 6. So 3 times 6 plus c. And I'm going to subtract from it 3 times 2 plus c. These will undo each other, and I end up with 3 times 6 is 18, subtract 3 times 2, which is 6, and I end up with 12. So if you try and see what this little operation has done, this chunk here, 18, that was this area. Everything all the way up to 6. And this chunk, the 6, right, like 6 wide, 3 high, that's 18 units. 6 units would be everything up to 2. 2 times 3 is 6. So I can get the area shaded in green by taking the area shaded in pink and subtracting the area shaded in blue. So this integral is generating the area of all the shapes underneath of that curve, and you're just selecting off the pieces that you want to keep and then the pieces you want to throw away. So to show you again that this works, I'm going to try and build a triangle using a line. So I'm going to erase this and we'll try that example. So if I switch to a linear function, g of x is x, if I were to sketch that for you, I need my x-axis, and I'll need a 1, 2, 3, and a 1, 2, 3, and just for ease of numbers, I'm going to go between x is 0 and x is 3. So if I sketch y equals x, that's just a straight line with a slope of 1. So it's something like this. And I'm trying to find the area between 0 and 3. So I want this area. Well, that's just a triangle, and it's a triangle that's 3 wide and 3 high. So the area should be 1/2 base times height. So it should end up being 1/2 of 3 times 3, which 3 times 3 is 9, divided by 2 is, it should be 4.5 when I'm done. So to do this with integrals, and again, I'm just doing it this way to have a number to try and match to. In order to get an area under a curve, I should just integrate that function over the x-axis between the values that it's asked me to consider. So you ask yourself, what function has x as its derivative? Well, x squared would give you the x part, and I need a 1/2 in front in order for the coefficients to work out, plus your c, evaluated between 3 and 0. So I'm going to have to do 1/2 of 3 squared plus c, subtract 1/2 of 0 squared plus c. 3 squared is 9, 9 divided by 2 is 4.5, plus c, subtract the c is gone. 0 squared is 0 times 1/2 is 0, and I end up with 4.5, which matches. Okay, so that's good. This is working. So my integration of the function that draws the top part of the shape, if I integrate that between the two locations I'm after, I end up getting the area that I would calculate otherwise with composite shapes. So I'm going to erase this, and we're going to do one more simple one that we can do an area to compare, and then we'll try some more complicated functions. So now I have a line that has a slope and it has a y-intercept in it. So I'm going to have to sketch that. Markers really start to scream as they become experienced. Okay, so 1/2 x plus 1 has a y-intercept at 1, and then it goes up 1 over 2, up 1 over 2, here, 1 over 2. So that's my line. That's g of x. And I'm trying to find the area between 1 and 4. 1, 2, 3, 4. Okay. So that's a little more complicated. This shape is a triangle on top of a rectangle. When x is 1, this is at 1.5 high. Here, so that will be 1.5 high. This is 2 units high. Is that right? 4 plus 2. Nope, that's 3 units high. So this is 1.5 up. And 1, 2, 3, 3 wide. So this area then is going to be a triangle, 1/2 base times height, plus a rectangle that it's sitting on top of. So that's going to be 1/2 of the base of this triangle is 3 wide. So let me make sure all my numbers are right. 1.5. X is 4, half 4 is 2 plus 1 is 3. Yep, so 3, and there's 1.5 already, so that has to be 1.5 up. 1/2 of 3 wide and 1.5 high, plus a rectangle that is 3 wide and 1.5 high, gives me a total of 1/2 of 3 is 1.5, 1.5 times 1.5 is 2.25. 3 times 1.5 is 4.5, giving me a total of 6.75. Whew, goodness. But allegedly, I can just integrate this line between the x values that I've identified, and I should be able to just spit this number out without having to do quite so much thinking or quite so much analysis on how to cut this up into shapes. So if I give that a try, I'm just going to integrate g 1/2 x squared, 1/2 x plus 1 dx, evaluated between 1 and 4. So you ask yourself, what function would have 1/2 x plus 1 as its derivative? Well, an x squared gives you the x, and this would have to be 1/4. 1/4, because 2 times 1/4 is 1/2. Plus an x to generate this part, plus the constant. And you might be saying to yourself, why do you keep writing down the constant? It just cancels out. And like, well, if you don't want to write it down and can remember that it should be there when you're not doing an iterated integral, that's fine. I'm just going to write it in for completion. So I need to evaluate this thing still from 4 to 1. So I end with 1/4 of 4 squared plus 4, subtract 1/4 of 1 squared plus 1. Oh no, I forgot the c's. Plus c minus c, whatever, it's gone anyway. 4 squared is 16. 1/4 of that would be 4. 4 plus 4 is 8. Don't even need that bracket anymore. 1 squared is 1. 1/4 times 1 is 1/4. 1/4 plus 1 is 1.25. And 8 subtract 1.25 is 6.75. Like, holy cats, that actually worked out. So, as complicated as I wanted to make this, I was able to get a matching area under the curve just by integrating the function and iterating the integral over the range that I wanted to use. So that was all well and good. Like, this method is fine as long as I can chop the shape up into rectangles, triangles, and circle segments. But as soon as I get into a more exotic function, I'm not going to be able to get away with that anymore. So I'm going to erase this, and we're going to try a function that I can't actually chop up like so. Alright, so this one, 4 minus x squared, that's a parabola that has a y-intercept of 4 because it's been shifted up 4. It's been flipped upside down, and it has not been shifted left or right. So if I were to sketch that, 1, 2, 3, 4, 1, 2. The vertex of that thing is here. Over 1, down 1, over 2, down 4. Like that. So I've been asked to find the area under this curve, under this parabola, between x equals 0 and x equals 2. So I'm after this. Now here's where this technique gets handy, because you can't actually chop that up into rectangles and triangles. You could get close to it, but you wouldn't be exact. You'd always have a little bit of extra space shoved in there as you tried to chop the thing up. So this integration process is going to give you exactly the answer. So once I've got this function, in order to get the area under this curve between these 2 points, I just need to integrate. So the area will be the integral of the function in question between the x values that were stated. So I have to integrate this. What function would give me 4 as its derivative? Well, that would be 4x. What function gives you x squared? Well, x cubed gives you the x squared part, and I'd have to have a negative 1/3 in front. 3 times a third would be 1. That technically should be there, but if you forget it, it doesn't really matter because we have an iterated integral, and I'm evaluating this from 2 to 0. So to get my area then, I'd have to do 4 times 2 minus 1/3 of 2 cubed plus c. Subtract 4 times 0 minus 1/3 of 0 cubed plus c. C minus c is gone, as it always is. 2 times 4 is 8. 2 cubed is 8. Divided by 3 is 8/3. That's 0, so that's it. 8 minus 8/3. And 8, if I get common denominator, that's 24 over 3. Subtract 8 over 3 would be 16 over 3 units squared. So the area under this parabola is exactly 16/3 of a square unit. So if these were x's were counted in meters, then this would be meters squared. If this was calculated in feet, then this would be feet squared. So this is a problem you've never been able to answer before. You couldn't find the area of a curved shape unless, or the area of any shape actually, unless you could chop it up into rectangles, triangles, and circles. But now you can do anything. As long as you can bind the function with one flat edge and one curved edge, all you need to do is integrate the curve and you'll have exactly the area involved. So we're going to do 3 more examples of this, and then I'll set you off to try the practice problems. So to sketch this one, sine curves go as high as 1, and they go as low as -1, and they repeat every 2 pi units. And the sine curve starts at 0, peaks midway, zeros, troughs, zeros. So that's sine x, and I'm trying to find the area between 0 and pi. So I want to find out how much space there is under this little lobe. So there's no way to write that as rectangles and triangles. It's the wrong curvature to use a circle segment. So I have a function that I normally wouldn't be able to get the area under until now, until I have this integration technique. So to get the area under this curve, right, it's bound by an axis and the curve, all I have to do is integrate between 0 and pi of this function. So you ask yourself what function has sine as its derivative, and that's cosine gives you negative sine as its derivative, so I need to make that negative, plus my constant, stupid constant, evaluated from pi to 0. So my area would be negative cosine of pi plus c, subtract negative cosine of 0 plus c. C minus c is gone. Cos of pi is -1. Subtract negative. Cos of 0 is 1. Negative 1 is 1. Negative 1 is plus 1. So the area is 2. Now that's kind of neat, right? Sine has all those horrendous values, right? Like non-repeating decimals and the only clean values, the closest to clean values you can get are like root 3 over 2 or 1 over root 2, all these terrible numbers. And this scale is on radians, right? Like that thing is pi wide. Pi is irrational. It doesn't have repeating decimals. But if you were to shade it in and figure out exactly how much area there is under one lobe, the thing takes up exactly 2 square units. Which is sort of a neat little contradiction, right? Something that's an irrational number wide can have a clean integer area. Kind of cool. But we're just following a pattern here though, right? Like you take the function, whatever it is, and you integrate it between these two values, and you get the area that's contained there. So 2 more examples to go. I want to find the area under this curve between these 2 points. So I'm going to have to sketch 1 minus cos x. All right, so this is a cosine function that has been lifted 1 and inverted. So I'm going to need a midline at 1. And I'm going to have to chop this up into units of pi and 2 pi, maxing out at positive 2. So this curve is going to do this. Good. So in order to do the area under this one, rinse and repeat, I'm going to have to be integrating the curve 1 minus cos x dx from 0 to 2 pi. And that should give me the area underneath this curve here. Everything there from 0 to 2 pi. All right. So ask yourself, what do you need to get 1 as your derivative? Well, that would have to be x. What do you need to get negative cosine as your derivative? That would be negative sine x. And I'm supposed to evaluate this from 2 pi to 0. So I'd end up with 2 pi minus sine 2 pi, subtract 0 minus sine of 0. Oh, plus c minus c, whatever. 2 pi. The sine of 2 pi is nothing. Subtract nothing. Sine of 0 is also nothing, plus 0. So this ends up being 2 pi units. All right. So there's 2 pi units worth of area under that. Let's see if we can convince ourselves that that is true. See this chunk here? This chunk is a half pi wide and 1 unit tall. So that area there is 1 times pi over 2 units worth of area, pi over 2. Now in the last unit, or the last example, sorry, we found that the area under this lobe was 1. That means that the area under one of these lobes is a half. So in this chunk there, I have 2 different pieces. I have the part in green, which has an area of 1/2. And I have this pink piece, which is the balance, right? The pink piece would be pi over 2 subtract 1/2, whatever that is. So I'm going to try and construct this number from the area of these pieces. So if I look at it, I've got this chunk here, which is pi over 2 minus a half. So I've got this chunk here. This piece here is another one, so that's 2 of these. I have this piece up here, which in the last example I found was 2 units. And I have this chunk down here, which is a rectangle that is pi units wide and 1 unit high. Pi unit wide times 1 gives me pi units. So if I were to add all that stuff together, I'm supposed to get 2 pi units worth of stuff. So double this. I just have to add all these chunks together. So 2 times pi over 2 would be pi. 2 times negative half would be negative 1. Plus 2 plus pi. Oh goodness, I think the area under this was 2, right? Yep, so that this would be pi over 2 subtract 1. Let's subtract 1. 2 times 2 would be 2. And so I end up with 2 pi units. So I was able to construct it with pieces with one tiny little algebra error, and I ended up getting the same number. So that's nice and consistent when it works out that way. So basically, you can get the area under any curve just by integrating it between these 2 x values. So I have one more example to do where we have to do a limit to actually get the area, and then we're going to try and figure out why this is happening. So this function was one of the ones you did back in curve sketching, so you'll kind of have to remember what it looks like. It has an x-intercept at 0. That's sort of where it starts. And then it has an x-intercept at 1, and it does something like this. So I'm after this area here. Now something funny is going to happen. It's area under the curve, or like under the axis instead of over the axis. So when you have that, the answer you're going to get is negative, right? It's un-area, or area located below the axis. So keep that in mind when we're going to get our answer. If I'm only going from 0 to 1, I'm really only after this chunk here. So in order to get the area, I should integrate between 0 and 1 the function x ln x. So that's an integration by parts. So I'm going to let p equal x, and I'm going to let dq dx equal, no I'm not, I'm going to let p of x equal ln x, and dq of x equal x. So my dp puzzle piece will be 1 over x, and my q puzzle piece will be 1/2 x squared. So this area should be q p evaluated from 1 to 0, subtract the integral from 0 to 1 of my q piece, my dp piece, dx. I'm just going to leave this here for a second. Squared ln x from 1 to 0. This ends up being the integral from 0 to 1 of x squared over x, that's just 1/2 x dx. And so a would be 1/2 x squared ln x 1 to 0, subtract 1/4 of x squared evaluated from 1 to 0.
Mr. Perry, call 524.
So this part here, I have a equals 1/2 of 1 squared ln of 1, subtract 1/2 of 0 squared ln of 0, minus 1/4 of 1 squared, subtract 1/4 of 0 squared. So if I scroll across this, ln of 0 is or ln of 1 is 0. 0 times 1, so that term is gone. This one here, a quarter times 1 squared would be negative a quarter. 0 squared times a quarter would be 0, so that's gone. Negative, negative would be plus 0. Now I have this. Ln of 0 is infinity, negative infinity actually, and this would be 0. That's an indeterminate form, so I'm going to actually have to take some limits to do this. So let me put that one in a circle for you. Uh-oh. Indeterminate form. So to solve this, I'm going to have to solve the limit of h going to 0 of 1/2 h squared ln of h. So if I were to do that, I'm going to try h equals, let's say, 0.1. So if I put in 0.1 there, I end up getting negative 0.023. Try it in your calculator. I did it in advance just to save us some time. But you should try this. Put a 0 here, or a 0.1 here and 0.1 there. Ln of 0.1 times 0.1 squared divided by 2 should give you this. And then if I tried h equals 0.001, I end up getting negative 0.000000691. And just for good measure, if I try 0.00001, I end up getting negative 0.4561115. These numbers, these are going away. So it turns out this thing vanishes to 0 if you use limits to solve it. So I end up with another 0 term, and my total area is negative 1/4. So this thing here, it's under the axis, so I should get a negative area, and I did. So that's encouraging. It turns out that even though this thing is generated by ln, which normally has very heinous returns if you plug numbers into it, gives you a nice precise value, right? Just a quarter. And even if my function has one of these funny things in it, right? When I try to evaluate my iterated integral, if I have a 0 multiplied by an infinity, I just need to use my limits technique and I can still spit out an answer, right? This shouldn't have been, you shouldn't have been able to evaluate that. But calculus techniques, this was the first one we did, right? Using limits. And then this one, the third one, integration, allows you to get an area under that curve when you otherwise really shouldn't be able to. So I'm going to erase this, and we're going to try and justify how an integral is giving you the area under a curve. Alright, so I've given you a function there. It's not a specific function, not one I can write with an equation. It's just this purple line, or pink line there. And I'm going to try and get the area under that curve. So the lame way to do this, and the way you would have had to do it up until you learned about the integration method, was you would have had to go and you would have had to chop this thing up into rectangles. And you try and wedge the rectangles in underneath of this curve. And so that one fits there, and then this one fits here. And the purists out there are looking at this diagram and saying there should be something about only touching on the left-hand side or only touching on the right-hand side, but I don't feel that's really necessary to prove the point. So I have a bunch of rectangles there. Now the height of those rectangles, or if we're trying to do area, the area of a rectangle is the length times the width. Right, that's just basic grade 9 math. So I'm going to look at this width here along the bottom. That's some jump in x, a delta x. I don't know what it is right now because I don't have a specific function, but it's some jump, and I make the same jump every time. So when I'm doing these areas, the width of these rectangles is really some jump in x. So the area of them is the length of that rectangle multiplied by this little chunk. Now if I'm trying to get the length of those rectangles, the length of them is determined by the height of the function. So if I pick a corner, if I pick the left-hand corner, and I plug in this x value there, then I get how long that triangle or rectangle is. So these lengths are really just the height of the function at that particular point. And so if I was trying to get the area under here, I'm not just doing the area of this rectangle or the area of this rectangle or the area of that one. My area is the function at the first x place plus the function at the second x place plus the function at the third one, dot, dot, dot. And I'm going to have to do an area for each of those rectangles. Now that's a bit tedious because I have 1, 2, 3, 4, 5, 6, 7, 8. I have 8 rectangles I have to write, and I'm already tired of writing it after only the third. So I'm going to shortcut this notation by using sigma. Okay, so there I go. Sigma just means add up a bunch of stuff. Add up some terms. So this little n is saying you have to add up the first one, then the second one, the third one, the fourth one. So if I were to do that, I'd get most of it, but I'd be missing this chunk here, and I'd be missing that chunk here, and that chunk, and that chunk. So I want to make this a better approximation. And the best way I can do that is to make my rectangles narrower. So I'm going to erase these. I'm going to try and draw in ones that are half the width of what I had before. So I'll do one like this, one like this, one like this, one like this. So if I made those rectangles narrower, the amount of error I'm getting has shrunk, right? Because there's more rectangles that are thinner, so they can wedge into the curve a little bit easier. Now, ultimately, if I wanted this to be perfect, right, because it's not perfect yet, the best I could do if I erase these is instead of doing rectangles that have some thickness, I could just start drawing rectangles with almost no thickness, just straight lines. And if I do this, just straight lines, up and down, up and down, up and down, because they're so thin, they can fit right up into that curve perfectly, and I'm getting zero error. So the way I make my area, so this would be approximately. The way I make it exactly is I take the limit as delta x goes to 0. And here, I was only adding up over 8 terms. If I add up to, if I put lines in there, right, how many lines of 0 width can I fit in 8 units? Well, that's an infinite number of rectangles that are this high and this wide. And if I did that, that would be the answer exactly. So what I've done then is I've said that the area under any shape can be calculated by calculating the area of an infinite number of rectangles that have 0 width. Now that's a wonky kind of idea, basically you're building this by doing pencil strokes along in order to fill in that area space. This is a bit clumsy, so we're going to modify this just a little bit. First off, back when we did the first principles derivative, when we had a gap that you could measure, you used delta x. When you let that gap shrink away to nothing, you replaced it with dx. So in the integration, this dx is the width of those teeny tiny little rectangles that has dropped away to 0. This is the function that I've been working with that determines the heights of those rectangles. And this is a summation, an infinite summation. So if I have a Greek letter sigma, right, for my summation, if I want to show that it's an infinite summation, I just need to use a different letter, right? So when it was delta, we used D. So that was a Greek letter, and we switched to a Latin letter. When it's a sigma, the equivalent Latin letter to sigma is an S. S for summation. But if you keep in mind that this stuff was cooked up in the 1700s, if you've ever seen a document from the 1700s, S's didn't look like that. S's were highly stylized. So the word, let's see, the word stuffed. The word stuffed would have looked like this. Where the S and the F were both very tall with this little hook on them. So this S in the 1700s would have looked like a highly stylized S, very tall, very thin. And so that's where you get this integration notation, is that thing in front, the little snake that you've been working on, practicing drawing for the last little while, is just an S for summation. And it means that there's an infinite number of terms being added together. So there's an infinite summation of rectangles that are this height and 0 wide. And if you do that, you end up generating the full area of the function under the curve. So I'm going to let you stew on that. If you go back to the practice problems, try and get the area into those curves, then you should be pretty good at this by the time you're done.